So today we're going to talk about the last method that we're going to learn to evaluate volumes of a solid. So this is section 2.3, cylindrical shells. So the first goal for today is we want to learn what's the method of cylindrical shells and how we're going to use it. And the second goal, we're going to compare the different methods that we've learned and learn how we're going to choose which method to use when we want to evaluate the volume of a solid. Okay, so what's different with this method? So in this method, the only difference is, if you remember the disk and washer method, for example, I had a function in terms of x and I did the integration in terms of x and everything was around x. That we revolved the function around x, everything bounds related, everything was in terms of x, for example. And similarly, if I had a y function, I would revolve it around the y-axis, or like a line y equals something, and I would evaluate it by integrating in terms of y. But what happens if I have a function in terms of x, for example, but I'm revolving my function or my region around the y-axis, or a line like y equals something? So here we're going to use cylindrical shell method. So let's look at some graphs and understand it better. So let's say that I have this region R and I have a function in terms of x. Here I want to revolve this region around the y-axis. So I have a function in terms of x, I'm revolving around in terms of the y-axis, so we're going to get this solid. Okay, so let's look at one rectangle in that region, see what happens if we revolve it around the y-axis, and then see how we're going to be able to find the volume. So if I have this rectangle with delta x, obviously, to be the width, this is my xi minus 1 and xi. These are the beginning and the end of the rectangle. Obviously, the height here is just f of x. Now, if you revolve it around the y-axis, you're going to get something called a cylindrical shell. So there's a hole inside of here. Now, if we take the whole region and I take different rectangles and I do the same process of revolving around the y-axis, I'm going to get the same exact shell for each rectangle. So this will create different cylindrical shell for the solid that we have. So here, taking the same things that we did before, we have a regular partition, we have a point in each subinterval, then we construct a rectangle over that subinterval with height f of x I star and width delta x. Okay, so now we have the components. I have different cylindrical shells inside of my solid. If I'm able to evaluate the volume for each shell separately, the volume for the whole solid here would be just the sum of the volumes for each shell. So how would we evaluate the volume for the shell? Let's take a shell by itself here and look. We said that what's inside is empty. So how about we take a cross section? If you take a cross section, you will get something that looks like this. A circle inside of a circle. So I have a hole here. If you remember from last time, the area for this would be just the area for the outer circle minus the area of the inner circle. So now the radius for the outer circle is just xi. Because if you look here, when you revolve it, the outer thing is just xi and the inner thing is xi minus 1. So that's why the radius for the outer is xi and the inner is just xi minus 1. So the area for this whole region S would be the area of the outer circle minus the inner circle, which is just pi xi squared minus pi xi minus 1 squared. And if you remember when we calculated the volume from last time, it's always the height multiplied by the area of the cross section. So let's look here. We know that the height is just f of xi star, and we calculated the area from here. Now if you take pi as a common factor, and then here you have a difference of 2 squares, so you can just factor it, and then let's multiply by 2, divide by 2. You'll see why this makes sense. Now my xi minus 1, this is just delta x from the definition. Now the reason why I wanted to have divided by 2 here, because if you remember, this is the formula of a midpoint of a certain interval. So this thing is just a midpoint of this subinterval, and it's the same as the average radius of the shell. So we can kind of approximate it by xi star, because xi star is just a point inside of your subinterval. So instead of writing this whole thing, you can just write xi star. Now this is going to be the volume for each one of these shells. So to calculate the volume for this whole thing, you just want to sum it, right? Okay, so here we're going to sum it, and we're going to get a Riemann sum, and I'll talk in a bit how like taking the limit of a Riemann sum is just what we want to get. But I want you to think about evaluating the volume for this cylindrical shell in a different way too. What if we cut our cylindrical shell and just flattened it out? So you're going to get this solid with, we know that the height is just f of xi, the width of it is just, or like the thickness of it is just delta x, and now the width of this rectangle is going to be 2 pi xi star. But why is that 2 pi xi, right? So if you look here, once you cut it, it was already a circle. So this 2 pi xi is just the circumference of a circle, which we know that it's just 2 pi times the radius, and we know that the radius here is just xi star. So if you want to find the volume of this shape, solid, is just width times height times thickness, so you're going to get this, which is exactly what we got when we did the cross-section method. Okay, so going back to the sum, once we sum over the volume for each cylindrical shell, we're going to get a Riemann sum. And the function here is 2 pi x f of x. If we take the limit as n goes to infinity, using the definition that we've learned, we're just going to get a definite interval from a to b of our function, 2 pi x f of x. So if we want to find the volume for any solid, when we have a revolution with a different variable, we're just going to use this formula. So this whole method, it's the method of cylindrical shells. So to summarize it in one rule, if we have a function that's continuous, non-negative, we have a function region R bounded by f, and the x-axis, we have the interval from a to b. The volume of the solid of revolution that we get from revolving R around the y-axis would be given in this formula. Okay, so like always, let's do an example so it makes more sense. So if we have R to be the region bounded by the function x squared and the x-axis on the interval from 1 to 2, and we want to find the volume of the solid of revolution around the y-axis. So whenever you look here, I have a function in terms of x. I'm revolving around a y-axis. Immediately, I know that I need to use cylindrical shells. We know that cylindrical shells has this as the formula for the volume. But let's look at the graph first. So if I have this graph, this is just x squared, and then from 1 to 2, from this function to the x-axis, I'll have this region R. Then once you rotate it around the y-axis, my graph is not accurate, so sorry about that, but you're gonna get something like this. Now applying the formula, I just have the bounds from 1 to 3, 2 pi x, then you multiply by your function. So my function is just x squared dx, and you integrate normally. Then upper minus lower, and you'll get your answer. Okay, so similarly, if I had a function in terms of y, and the region is between that function and the y-axis, then I'm revolving the region around the x-axis. We need to use the cylindrical shells method, but we have the volume in terms of y. That's it. Okay, so let's do an example. If we have g to be 3 over y, so that's my function g, and the region is between g and the y-axis on the interval from 1 to 3, so that would be our region q. Then if we're revolving around the x-axis, we're going to get something that looks like this. Again, my graph is not accurate, but it's just like a sketch. So we know that we have a function in terms of y, we're revolving in terms of x, so I have to apply cylindrical shells. You take the bounds, if you look, it's just from 1 to 3, then pi, 2 pi y, 3 over y, which is your g of y. So you're gonna get 12 pi. Okay, so far it's pretty easy, right? Because I'm just revolving around my x and y axis. Now what happens if we have a revolution around a certain line? So for example, x equals 2, y equals 3, and so on. So it's not a lot of difference here. My only difference is the radii of the cross sections that we're taking. So we have some sort of shift, like I have something added to my radii. So here, let's assume if I have a line x equals negative k, where k is just any positive number, and I want to revolve my region around that line. So here, the outer radius, you just add a k, and the inner, similarly, you just add a k. Substituting that back in the formula where we got the volume of the shell, you're going to get the same exact thing, but with an extra k. So here, instead of having this to be my midpoint and estimating it to be xi star, it's going to be xi star plus k. So when you take the volume using like Riemann sums and the limit, you're just going to get 2 pi xk plus x plus k times f of x. And similarly, if you did it with y, you just do y plus k. Oops. So it's not a big difference. It's just like you add an additional number to your radii. Okay, so let's try it. If I have a graph of x squared and the x-axis, so the region is bounded by these two on the interval from 0 to 1, and we want to find the volume of revolution around x equals negative 2. Okay, so although this line is x equals negative 2, that does not mean that I'm revolving around something in terms of x, because here the line x equals negative 2 is perpendicular to your x-axis, which is the variable that you have. So whenever you have like a line perpendicular to the axes that you're trying to evaluate your function at, you need to use cylindrical shells. Okay, so let's look here. I have my function x squared from 0 to 1. If you try to revolve it around this line, you're going to get something kind of like this up. Again, it's not accurate. Then if you take a cross section, you're going to get this kind of circle. If you take the radii radius of this? Let's look here. So the distance between the center of the circle to the end of the circle, it's going to be 2, because this is the distance from -2 to 0, plus the distance here, which is from 0 up to your function x squared. So this distance here is, oh sorry, this is not x squared. This is like a distance x, right? Because you're moving along the x-axis. So from 0 to x, this is just x. So this whole distance is just x plus 2. So this is where the x plus k comes from. So to evaluate the volume here, I'm just going to take the integral from 0 to 1 using the rule of cylindrical shells. We have 2 pi, but instead of x, I have x plus 2 here, times your f of x, which is x squared dx, and you can evaluate it easily. Sorry, this is 1, not 2. So yeah, x cubed plus 2x squared d of x, and just antiderivatives, and you find it easily from 0 to 1. So 1/4 plus 2/3 minus 0, and so on. Okay, now what if we have two functions instead of like a function and an x-axis or a function and a y-axis, and we're revolving that? So let's look here. I have function f equals x, g x squared from 0 to 1, and we want to find the volume of the solid of revolution around the y-axis. Functions in terms of x revolving around y, so we have to have a cylindrical shell. So the only difference here is, since I have two functions, my height, it's not going to be just f, because if you take a rectangle here, we're going to have delta x as my width, but the height here, it's going to be the difference between f minus g. In the above graph, like when we had like f, for example, when you took a rectangle, this height was just f of x, because this is f of x minus 0, so the height is just f of x. But the height of this rectangle is going to be f minus g. So since when we're doing like the volume using the cylindrical shells, it's just from a to b, 2 pi x, which is my width, times f of x, which is my height. So instead of f of x, we're going to have f of x minus g of x d of x. Okay, so now my a and b is just from 0 to 1, 2 pi x, and then f of x, x minus x squared dx. If you distribute, you're going to get x squared minus x cubed d of x from 0 to 1. And upper minus lower, you're going to get the value of your integral. So it's quite easy, I would say. It just, sometimes it's a bit tricky when you have like different functions, you don't know which method to use and stuff like that. So now I'll summarize all methods and we'll see which method works when. Okay, so let's look at this table. If we have a volume of solid of revolution and we're revolving around the x-axis, the desk method is always used when we have no cavity in the center. We don't have a cavity, we're integrating in terms of x, so my function is in terms of x, and we're always revolving around the x-axis. So a function of x with revolving around something in terms of x. Now the rectangle is going to be vertical since it's in terms of x, and then this is a typical region. You have a function f, upper, and then the lower is just the x-axis, and that would be your rectangle. Now the washer method is kind of similar. I have functions in terms of x. I'm revolving around an x-axis, but we have a cavity in the center. So this is helpful when you have like an upper function and a lower function. So if you have like an f and a g and the region in between, once you have a rectangle and you revolve it around the x-axis, for example, you're going to get a cavity inside of your solid. So this is where the washer method is helpful. And lastly, the cylindrical shell method, like we said, let's say I have a function in terms of y. Here, the revolution would be around a y-axis or like something different. Yeah, so here, like if I have a function in terms of g, normally the revolution would be around the x-axis and so on. So here, the rectangle would be horizontal, and this is what a regular graph. So I'll have like a function of g and a region. This is my rectangle, and I'm revolving around the x-axis, for example. Here, I could either have a cavity or I could not have a cavity. It depends on the question. You just pay attention. If I have a function in terms of g, in terms of x, but I'm revolving around the y-axis, for example, or if I have a function in terms of y and I'm revolving around the x-axis, this is where the shell method comes in handy. So let's look at this example. We want to select which method is best to evaluate the volume of solid of revolution revolving around the x-axis, and we have these two functions. Okay, so we have two functions and we have the x-axis. So let's look at the graph of these two functions first. I have x squared, 2 minus x squared between these two functions, so I'll have this region R. So let's find these points of intersection. Once you find the points of intersection, you equal the functions, you solve it, you're going to get -1 and 1. So that's why these are my starting and end point of the region. Okay, so let's back up. I have functions in terms of x, and I'm revolving around the x-axis. Same variables, then this means I'll either use the disk or the washer method. But which one would be useful here? If you look back, the typical region for a washer is upper and lower function. So I think we're going to need to use the washer method here, right? Because we're going to have a cavity. Once you revolve this around the x-axis, this part here would create a cavity, and this part here would create a cavity. So that's why we're going to need to use the washer method. The formula for the volume of a washer method is just pi f of x squared minus g of x squared dx. And now we just substitute. So here my f of x is the upper function, which is the purple graph. So we're going to have -1 to 1 because these are starting and end points of the region. Then f, we said it's the upper, so it's the purple, minus g, which is the lower in blue, and you square them both and subtract, and you evaluate. Okay, so that's all for the methods of evaluating the volume. My only recommendation here is practice doing different examples, so you'll notice like a pattern, or like when I have these functions, I'll do this. If I have a cavity in that way, I'll definitely use the washer or the disk, and so on. So it's all about practice and getting used to using all of these formulas. Okay, so we have some suggested problems from section 2.3. If you need some extra practice, you can do them. If you have any questions about this, you can just email me about it, or yeah, just let me know and we can do like a Zoom meeting, or I'll answer you over email. And if you go to Lumen Homework 2, you can do these problems. I hope you have a great day and best of luck.